Hello, I'm Sadaf from University of Amsterdam. Until now, you might have heard about the successes of neural networks. However, in this work, I will introduce you with the scenarios in which neural networks fail and how we counter these failures. This work is done in collaboration with Jan Henrik from Bosch AI Research and my advisor Arnold Smulders. I will start with the motivation behind this work. Neural networks have been deployed in almost every field of life, ranging from autonomous vehicles to healthcare and also in finance. Although the performance of neural networks is on par with humans or even exceeds humans, they tend to fail in the presence of perturbations. Previously, a large body of research in the field of robustification against perturbations have focused on robustifying neural networks against artificially created perturbations, also known as adversarial perturbations. These images show the examples of the performance of neural networks in the presence of adversarial perturbations. The example on the left shows failure in the classification. We can see that the clean image, which was classified as pneumothorax with the confidence level of 99%, now the confidence of the classifier dropped to 0%, while the example on the right is for failure in the semantic segmentation. We can observe that for a clean image, the network performed correct segmentation, while for the perturbed adversarial image, it failed to segment humans on the road. Such failures could lead to consequences. At the same time, the research also shows that deep neural networks are not even robust to small natural perturbations, for example, Gaussian noise, snow effect, or streak effect in the medical images. But there is very little focus on robustifying the networks against such natural perturbations. We argue that adversarial perturbations introduced in previous slide are difficult to be found in the real world, and natural perturbations are different in nature from these adversarial perturbations. Therefore, neural networks should also be robustified against natural perturbations. Hence, in this work, besides robustifying classifiers against adversarial perturbations, we also robustify them against natural perturbations. In the methods section, at first I will introduce how we generate both adversarial examples and natural perturbations, and then the robustification of classifiers against them. Adversarial examples are generated by adding carefully crafted noise in the images, such that the class of the image changes while keeping the image visually similar to the clean image for a human being. For example, in this image, when a carefully crafted noise is added to a clean image belonging to the class Rufous Hummingbird, its class changed to Green Kingfisher, while we humans can still classify this image as Rufous Hummingbird. Next, in this work, we utilize 6 natural perturbations. Natural perturbations generated by satisfying 2 properties that are the drop in the accuracy of a classifier with the natural perturbation will be same as the drop with the adversarial perturbations for fair comparison among them. Secondly, the images with the natural perturbations should be classified correctly by the humans. After constructing images with perturbations, we also robustify classifiers against these perturbations. In the top row of this figure, we see standard neural network-based classifier training and testing procedure. We can see on the top right that when an adversarial perturbed image is introduced to the standard network, the image gets misclassified. But in the second row, we can see when we train the network on adversarially perturbed images, the network becomes robust against these perturbations. And now the classifier classifies the images correctly in the bottom right corner. Similarly, on this slide, we can see on the top right that when a naturally perturbed image, for example, image with the snow, is introduced to a standard classifier, it also fails to predict the correct class. But in the second row, when we train the network on similarly perturbed images, the network becomes robust against these perturbations and classifies the images correctly in the bottom right corner. Now I will go over the experiments and results. We conducted our experiments on 5 different image datasets of different sizes and granularities. As a first step towards our experiments for fair comparison among different types of perturbations as well as among different datasets, we standardized the comparison by dropping the performance to the same level. In the plot, x-axis shows all the 5 datasets and y-axis shows the change in the accuracy. The performance of a standard network on clean images for each dataset is normalized and shown on line 0. After this, the accuracy for each perturbation on each dataset is dropped by 10% to enforce fair comparison. Next, we compare the performance of adversarially robustified networks in the figure A with the naturally robustified networks in figure B when tested on clean images. We can clearly see from the plots that when the network robustified with adversarial perturbations is tested on clean images, it leads to the drop in performance on them, except the coarse-grained CIFAR10 dataset. On the other hand, when robustified with natural perturbations, in most of the cases, there is no drop in the performance, and whenever there is the drop, it is minimal. In this slide, we contrast the performance of adversarially trained networks in figure A with naturally trained networks in figure B on seen perturbations. That is, the networks are trained and tested on the same types of perturbations. By comparing both plots, we observe that although adversarial training helps against adversarial perturbations, however, the improvement in the performance with natural perturbations training against natural perturbations is better. Finally, we present the comparison between adversarially robustified networks in figure A and networks robustified with natural elastic and occlusion perturbations in figure B on unseen perturbations. By unseen, we mean that the perturbations that are not seen during the training. Due to the time limitation, I will only present the results for elastic and occlusion perturbations. Results for the rest of the perturbations could be found in our paper. We can observe from the plots that adversarial training on unseen elastic and unseen occlusion leads to further drop in the accuracy. On the other hand, elastic and occlusion almost completely recover the performance on adversarial. The line plots with a plus symbol in the figure B shows the performance on adversarial perturbations. Additionally, elastic and occlusion perturbations also generalize to other unseen perturbations. Finally, to conclude, we conducted a fair comparison between adversarially robustified and natural robustified networks. Our results showed that natural perturbations, they generalize to clean images. Furthermore, robustification with natural perturbations perform better on seen natural perturbations as compared to adversarial perturbations on seen adversarial perturbations. Finally, elastic wave and occlusion showed the best general robustness when evaluated on unseen perturbations. We conclude that although general robustness is hard to prove, natural perturbations training always showed better robustness than adversarial training. Thank you.